Welcome to a very special episode of Twisted Signals. Today, my voice will be entirely rendered in the sound of a saxophone using timbre transfer by the Google Magenta Research Group. Just kidding. Okay, today we are going to be talking more about how computers represent signals. So, in our previous lecture, we were talking about sampling. Here we see a signal that repeats itself 2 times per second, and we sample it 4 times per second, and this allows us to accurately reconstruct the frequency of this signal. This is known as the Nyquist theorem. The Nyquist theorem tells us that if we want to accurately reproduce some frequency inside of our system, the sampling rate needs to be double that frequency or higher. So when we're designing a system, we want to look at what is the band limit of the frequencies that we wish to accurately represent, and then our sample rate will be determined by that, where the sample rate will be at least twice as high as the highest frequency. So that's how we determine how frequently we're going to sample a signal when we want to digitize it. But what we haven't talked about yet is how we actually encode these samples in a computer. So computers are digital systems. Everything is ones and zeros. The accuracy of these measurements is determined by how many bits we use to encode these values. So 1 bit is 0 or 1. There's 2 possible values. But if we encode a sample using 2 bits, we double the range to 4 possible values. We have 0, 0, 0, 1, 1, 0, and 1, 1. And every time we add 1 more bit to the measurement, we double the range of possible values that could be encoded. So 3 bits gives us 2 to the power of 3, which is 8 possible values. 4 bits gives us 2 to the power of 4, and so on. So as we look through my list of bit depth measurements here, you'll eventually see some ranges that might start to look familiar to you. If you have done any amount of computer-based music production, this is a number that will be maybe strangely familiar to you. You might have noticed that a lot of software synthesizers, the ranges that you can set things between is frequently between 0 and 127. And you might have wondered, like, what's special about that number 127? Why is that always the maximum on these software synthesizers? This is because historically, in the world of digital music production, MIDI has been the main protocol for how we transmit messages related to electronic music. MIDI stands for Musical Instrument Digital Interface. It is this protocol that was developed in the 1980s, and MIDI is a 7-bit protocol. So the maximum range of values that can be encoded in a MIDI message is 128 possible values. So including 0, that gives you 0 to 127, and that's why to this day in the world of electronic music, you always see this range of 0 to 127. You'll see this quite a bit when you're making max patches. A lot of objects, like if you make a new slider, the default range of that slider is 0 to 127, which seems like kind of random, but this is why. It's all going back to this history of MIDI being a 7-bit communication protocol. 8 bits of data gives us 256 possible values in the world of computer science. 8-bit data is frequently called char data because you can use it to represent characters, text characters. So 256 possible values is enough to encode every possible character in the alphabet and numbers and symbols and so forth. A lot of first-generation home video game consoles were also 8-bit systems, like the original Nintendo Entertainment System was an 8-bit machine There was 8 bits of color values, 256 possible colors. The sound that was synthesized was on an 8-bit system. And also all the data was 8-bit. So in the original Zelda game, if you've played this, maybe you remember that the maximum number of rupees that Link could acquire was 255 rupees. So that's because they were encoding his wealth using 8 bits of data. Okay, moving beyond 8-bit, 16-bit might be familiar to you. This is actually the bit depth that we use for the samples in CD quality digital audio. Now, some of you who are watching this video might not know what a CD is, but this was a popular sound recording format for digital audio. It was the first widely used digital audio distribution format. And it was decided when they developed this protocol that 16 bits was a good enough bit depth for the range of sounds that you might want to put on a music recording. And we'll talk about why 16 bits actually is a pretty good range for audio. 24 bits is also very commonly used in different ways. You might have heard about 24-bit color. We'll talk about that. Also, some digital audio is 24-bit, which is an even wider range of amplitudes than you get from 16 bits. So 24-bit audio is used quite a bit in more professional environments. If you're producing a digital audio recording with musicians or you're making a field recording outdoors, 24 bits is a range that gives you an even wider possible range of dynamics that you could record. 32 bits are often referred to in computer science as long ints, or sometimes just ints. And that gives you this huge range of possible amplitudes here. I think that's 4,294,000,000 possible values. And then 64 bits gives you this very large number. This is the maximum range of a 64-bit system, and a lot of contemporary computer operating systems are 64-bit. So let's talk about digital audio and how we might want to choose a bit depth for digital audio. To understand this, it's helpful to know what a decibel is. If any of you have done sound production or sound engineering, decibels are units that people talk about a lot when they're talking about the loudness of something. But it's not particular to sound. Decibel is just a way to express the relationship of two quantities, where you have one signal and you have another signal, and you want to express the difference between the two of them. A decibel is a way to do that. And specifically, mathematically, here's the formula. 1 decibel is equal to 10 times the base 10 logarithm of the ratio of power 1 over power 2. Now, the power of a signal is directly derived from its amplitude squared. So if we do some simplification of this to think of it in terms of amplitudes, 1 decibel is equal to 20 times the base 10 log of amplitude 1 over amplitude 2. And this is why we're about to conclude that 16-bit digital audio gives us a very good dynamic range when we're talking about human hearing. Okay, so 20 times the base 10 log of 2 over 1 is roughly equal to 6. Let me actually try to do it on my computer here. Yeah, so 20 times the log of 2 gives me 6.02. So let's just call that 6. So this means that if we double the amplitude of a signal, it's going to be increased by 6 dB. Okay, so let's go back to the previous slide. Now that we understand that doubling the amplitude of something is an increase of 6 decibels. Let's go back here and look at how we can represent samples using bits. Every time we add a bit, we are doubling the range of possible amplitudes. So, in other words, we're adding 6 decibels of dynamic range to that system. So, a digital audio system that has 16 bits, the dynamic range in terms of decibels is going to be 16 multiplied by 6 decibels. So we have this dynamic range of 96 decibels if it's a 16-bit digital audio system. So here are some examples of the loudness of sound in terms of decibels. So decibels, this is the most common unit for measuring loudness. And specifically, this is a specific flavor of decibels known as dB SPL, where SPL stands for sound pressure level. So here we see some very, very quiet sounds. So like whispering is 20 decibels. And as we go down the chart, we see some louder sounds. So here is like a chainsaw. Here, you know that old people made these charts when you see the word disco as an example of a loud sound. So a disco is 120 decibels. And you can also start to see here that once you go above a certain level, you actually start to do damage to your hearing system if you're exposed to it for beyond a certain number of hours per day. So according to various regulations, you should not be exposed to a signal that is above 105 dB SPL for more than 1 hour per day. Anything beyond that would be considered dangerous and you could damage your hearing. And here at 160 dB SPL, your eardrums would instantaneously burst, so I would say that's too loud. Apparently, according to this chart, 190 dB SPL is the loudest possible sound. Okay, so we determined that a 16-bit digital audio system has this dynamic range of 96 decibels. So let's say that we wanted to produce recordings that have a really wide dynamic range. Dynamic range refers to the difference between the quietest possible sound in your system and the loudest possible sound. So let's say that the quietest possible sound that you wanted to have in your recording is a whisper. So that's pretty quiet. With 16 bits, we could go all the way from whispers, which are 20 dB, all the way up to 116 decibels. So 116 would be above the level of pain. So that's a perfectly good dynamic range for digital audio. If you can go as quiet as whispering all the way up to the threshold of pain, that's going to be a very good range of loudnesses that you could encode with a 16-bit digital audio system. Okay, let's talk about colors and how computers represent colors. So colors are frequently broken down into different planes of color values. Using red, green, and blue combined together in different levels, we can create any color that people can see. So here we see a representation of how computers encode these values in planes of data, where we have red, green, and blue on separate planes that are sort of summed together to create all the different colors. And then there's typically this fourth plane as well, which is alpha. Alpha is sort of like an opacity layer. So the alpha layer could make certain parts of the image transparent and other parts of the image fully visible. So here we see an image that has red, green, and blue pretty clearly separated in different parts, and then there are certain parts of this image where they're combined, like the areas of the image that are yellow or white, we have red, green, and blue mixed together. So if we separated these out into those different planes, you have your red part of the signal, your green, and your blue part. So let's talk about the bit depth that we would want to use on these three different layers, red, green, and blue. The human eye can differentiate about 7 million different colors. So we want the possible ranges that could be created using red, green, and blue added together to add up to above 7 million, if it's going to accurately cover the range of human vision. So you might have heard before about 24-bit color. Let's look at how many possible values you can get with a 24-bit system. It's going to be 2 raised to the power of 24. You get 16,777,216 possible values with a 24-bit system. So 16 million is better than 7 million. So 24-bit color is going to be more than enough to cover the entire range of human vision. And because we're dividing this up between a red, green, and blue plane, we can divide up that 24 bits of data into those three planes. So what we do is we use 8 bits of data for red, 8 bits for green, 8 bits for blue. So 8 plus 8 plus 8 gives us 24, and that's 24-bit color. So when we are representing color values, we typically use 8-bit data on every layer of these planes. So we'd have 8 bits for alpha, 8 bits for red, 8 bits for green, 8 bits for blue. And that's going to be enough of a dynamic range to cover the entirety of human vision. Okay, let's look at some of this in practice. Okay, so here is a nice max patch. We are going to again use this degrade object to degrade the accuracy of our system, but this time we're going to use the rightmost inlet on degrade tilde, which is going to allow us to scale the resolution of the sound system in terms of bits. So currently this is set to 24 bits. 24-bit audio is going to be like a huge dynamic range. And let's listen to this 24-bit sine wave. And let's make it maybe a little bit more high frequency. Okay, so here's a nice 24-bit sine wave. It sounds so good. Let's start to degrade it by lowering the resolution of the samples. So here are 16-bit samples. Still sounds nice. And we're not really going to hear any distortion until we get into the lower range. When we go from 10 bits to 9 bits, if you listen closely, you might actually hear a little bit of noise start to enter the signal. And I think you can pretty clearly now start to hear some distortion now that we're down at 7 bits. So once we get really low, you can even see this on the oscilloscope. Our nice smooth sine wave is starting to look like a staircase. When we have a 2-bit system, there are only 4 possible values, and you can see those 4 bits on our scope now. It's just 1, 2, 3, 4. And if we have a 1-bit signal, this is now just a square wave, right? Because the signal is either high or low. So we've converted our sine wave into a square wave. So there's lots of examples of this being used as a creative technique in the world of experimental and electronic music. And anybody who's producing music in a kind of like chiptune style is emulating those early 8-bit video game consoles where they actually just had an 8-bit sound system. So all that chiptune style stuff is going to be emulated by artificially lowering the bit depth of our system. In the world of music production, this is sometimes called bit crushing. A interesting example of this is a piece by an artist named Tristan Parrish, who has created a really amazing portfolio of music that's all encoded with just 1-bit systems. So this was a recording that Tristan Parrish produced called the 1-Bit Symphony. It came in a CD box, but there was no CD. It was just a battery with a 1-bit chip that would play the pieces that were composed for it. So let's listen to a little bit of the 1-Bit Symphony. Let's look at breaking images apart into their red, green, and blue components. So this subpatcher here is going to take the image from my camera and break it up into red, green, and blue layers that we can look at from different angles. So these here, this is sort of like a literalization of the concept of having red, green, and blue in different planes. When you add together the red, green, and blue components of the image signal, you see full spectrum color. And then we can sort of break them apart and look at the individual red, green, and blue components that together create full color images. And this little demonstration is using this one object that comes from the jit.mo package. So you should check that out using the package manager, which is here, the package manager. Okay. In Jitter, the simplest way to think about these arrays of color values is matrices. So a matrix in Max is going to be a multi-dimensional array of data. And when we're talking about video, this is typically color data. So jit.matrix is the basic object that allows us to operate on jitter matrices. And it's going to have these arguments very typically, where the first number is the number of planes in the jitter matrix. So that's going to be our alpha, red, green, and blue planes. The second argument is going to be the type of data that is in this matrix. So char, as we mentioned, is going to refer to 8-bit data. So that gives us 2 to the power of 8, 256 possible values for each of those 4 planes. So if you add together those 8 bits for red, green, and blue, that gives you 24-bit color. Plus you have the 4th plane of alpha values, which is going to be kind of like your transparency layer. And then the next 2 arguments are going to refer to the resolution of every plane. So in this particular example, each plane is 320 pixels wide and 240 pixels tall. You can also specify these things using attributes. And when you do them in attributes, you can do them in any order. So here we have the plane count set to 5. We have a different type of data stored in this one. This one has long ints. And we have a much smaller resolution. So this is 4 by 6. So let's look at some examples of this. Okay. In this patcher, we are playing a movie. This is the jogging scene from 2001. So jit.movie is outputting these color values as a 4-plane matrix where we've got alpha, red, green, and blue. And here I'm using an object called jit.cellblock, which is sort of like a spreadsheet for jitter matrices. And this message shows me all 4 planes at once. So we see the alpha plane, and you'll notice that the alpha plane is set to full opacity everywhere. So every pixel in this matrix is fully visible. And then we have the next 3 values that are actually varying, and this is the color value for every pixel. So we see the red, green, and blue value for every pixel, and you can see them varying over time as we watch all the individual frames of this video being played. We're also printing out what comes out of this jitter matrix, so let's just look at this. Let me click on this button. And we're printing this to MOV, so you can see MOV is giving us this message that says JIT matrix, and then this randomly generated name, and this refers to the piece of memory in our computer where this array of color values is being stored. Here we have a very handy object for when we're doing jitter matrix stuff. This is the FPS GUI. And if we click on this drop-down menu, you can get some statistics about your jitter matrix. So here, the first one shows us the frame rate that we're getting. So this is 20 frames per second. We can see the data type in this matrix. So we have char data, that's 8 bits of resolution per plane. We can see the dimensions of this video are 1280 by 576, so that's just the resolution of the QuickTime movie that I've loaded into this player. We've got 4 planes for alpha, red, green, and blue. And then here's the name. This is that random looking name that's getting printed out, which just refers to that piece of memory. Now we're taking the output of jit.movie and we're running it through jit.matrix, where we can do some basic matrix operations on it. And actually by default, jit.matrix just passes the input to the output with no change at all. So if we look at the FPS GUI down here, we should see basically all the same information. We're getting the same frame rate, we have the same data type, we have the same size, the same number of planes. The only thing that would be different in this case is, I think, the name. So this has one randomly generated name and this has a different one. So these are both being stored in 2 different pieces of memory. So if we wanted to change this matrix in any way, we could look at this object. This is ATTRUI. It's an attribute inspector. I frequently refer to these as attruies. So if we click on this attrui, you can look at all the different attributes that apply to this object. So we can look at the dimensions attribute, and using the values that appear next to this attribute, you can change things. Here's the name. Here we could give this a different name. Let's call it Dave. Okay, so we have renamed this matrix Dave, and you'll see we're actually printing it out now. So instead of having a randomly generated name, this matrix has a specific name. Its name is Dave. Let's try to change the resolution of this by going to DIM, and actually this isn't going to work. I'm like trying to change these numbers and I can't. This is because we have to first go to the adapt attribute for a matrix and set that to 0. So when adapt is set to 1, the matrix is going to resize itself to match the incoming signal. So the dimensions of this matrix were being set by the matrix that comes into it if adapt is set to 1. But with adapt set to 0, I can now go to my dimensions and we can change the dimensions of the output matrix quite a bit. So let's just make it there. Now it is 4 pixels wide, but it's still 576 pixels tall. And you can see here now we only have 4 columns of data in this matrix. Let's make it 4 by 4. Okay, so we have converted the incoming matrix, which had this resolution, into a much smaller matrix that has 4 by 4 resolution. Now, you might notice that this doesn't actually look like 4 pixels. It kind of is getting smoothed out. So jit.world will, if you give it a very low resolution image, it will kind of like up-res it. And by default, it's going to smooth out the values between the low resolution pixels. So if you wanted to actually see this as the blocky looking pixelated image that it actually is, we would need to sort of manually up-res it. So we can do that by making a new jitter matrix. And we're going to up-res this matrix, so we need to set adapt to 0. And then we can manually set the dimensions of this to, let's make it 1000 by 1000. And if I hold down Shift, I can just kind of catch the signal in there. And now we've up-resed it, and we can see this kind of like high resolution interpretation of a very low resolution matrix. We could make this like 2 by 2. So there's our scene from 2001 rendered as a 2 by 2 matrix. And then finally, let's just look at some of these different types of data that you can put into a matrix. And we're going to do this by generating noise using jit.noise. So the jit.noise object creates random values, and you can specify this attribute, which is the data type. So when the data type is char, you're going to get char data in the range of 0 to 255. When it's long, you're going to get these, is this 32-bit? I think these are 32-bit long integers. So you're going to get this like huge range of possible integer values. And then there's 2 different flavors of floating point numbers you could get. You could get 32-bit floating point numbers if you say float 32, and you can get 64-bit floating point numbers with float 64. Okay, thank you for joining us. That's all I got for you. I'm going back into saxophone mode.